Good morning, everybody. My name is Matteo Ripoli, and my thesis is titled Stability Analysis of Magnetized Plasma Flows for Space Propulsion. My supervisors are Mario Merino and Eduardo Edo, and my thesis is focused on the study of instabilities and turbulence in our plasma thrusters, which behave as partially magnetized E cross B discharges. E cross B means that the electric and magnetic fields are perpendicular one to the other, while partially magnetized refers to the fact that electrons gyrate around their gyrocenters, while ions are almost unmagnetized and they follow inertial trajectories. These discharges are known to be subject to unstable oscillations, which might develop into turbulent phenomena and cause the transport across magnetic field lines of charged species. But how do we study it? The first route is the one through linear and quasi-linear models, in which one assumes the perturbations to be small, and they're usually used to study the onset of instabilities and the later development of weak turbulence, so the nonlinear interaction of this small perturbation one with the other. But usually they need saturation criterion to close them. Or one could go through the fully nonlinear route, but in this case, usually numerical methods are required, and among the many, we will talk about the particle in cell code. So the first part of my thesis focused on fluid local linear analysis of instabilities in a magnetic nozzle. And the magnetic nozzle is the accelerating part of an electroless plasma thruster. So again, we assumed small perturbation, and we described our plasma as a two-species fluid. And to do this, we had to put as a closure to the velocity distribution function. We assumed our oscillations to be isothermal. It is known from literature that instabilities are usually caused by the relative drift between charged species, and gradients are usually the cause behind these interspecies drifts. But in a magnetic nozzle, the gradients are even more complex, because usually in literature the only gradients that are considered are the ones perpendicular to the magnetic field. But in our case, due to the complex magnetic topology, we had to consider both perpendicular and parallel gradients. So this allowed us to derive a new dispersion relation and to generalize also some of the instability criterion that can be found in the literature. Once we found the unstable modes, we then applied quasi-linear theory to study how these growing modes were affecting the second-order flux, which would later affect the background plasma and the equilibrium. And what we found out is that the sum of the components of this second-order electron flux, which have been plotted on the upper right, they caused an outward electron flux, which was going against the gradient of the density over the magnetic field, which instead is plotted on the bottom right. And in the second work of my thesis, we actually went through a kinetic approach this time. So we were actually studying oscillations of the velocity distribution function. And this allowed us to retain particle-wave interaction effects, and also resonances were now inherently included in our model. And what we found out is that there is a particular resonance in the long wavelength regime between quasi-neutral waves and electrons drifting due to inhomogeneities in the magnetic field. And this sort of resonance gives rise to a particular mode which grows with the gradient in the electron temperature, and for that we call the electron temperature gradient mode, which offers a kinetic log wavelength alternative to other short wavelength models which are usually used to justify instabilities in our thrusters, for example in the Hall thruster. And in this figure in the bottom right, you can see here in the center the parametric region of instability for the for the classical Simon-Ho instability, parameterized against alpha and delta, which depend respectively on the gradient of the density and of the electric potential. And then on the left and on the right, instead, you see kinetic modifications to this parameter, to this instability, depending on beta. And beta instead depends on the gradient of the electric temperature. So this kinetic addition changes quite dramatically the instability region extension. And the third part of my thesis instead now is focusing on the development of an alternative particle in cell scheme, alternative to what? To the classical one, which relies on finite differences, in which particles are first weighted on a grid, then fields are computed on the same grid, and then are interpolated back on the particle. And this interpolation from particle to grid and from grid to particle can introduce some numerical artifacts such as spurious heating. But since our discharges are cylindrical, one can actually take an advantage out of this and could expand the fields in the azimuthal direction as a superposition of periodic functions. So actually they can be expanded as Fourier series, so that our particles can be weighted on the spectral basis functions, and then the fields, once they are recomposed, they can be evaluated directly on the particle position, so avoiding the numerical artifacts due to interpolation. And this sort of scheme is called particle in Fourier. So in our first work with this scheme, we actually developed a grid in the radial direction, and instead we treated the azimuthal direction spectrally. So mixing finite differences and particle in Fourier. And this allowed us to unravel a 2D problem into a series of 1D problems. This is due to the fact that Poisson equation is orthogonal. So each mode can be solved independently up until the moment that it is reconstructed. Because once we have all the modes of the electric potential, we can reconstruct the electric field at the grid, interpolated on the radial position of the particle and evaluating it exactly on its theta position. Our first application case was a pending discharge, where ions and electrons are injected non-neutrally in the center. What we found out is something that is known in the literature, which is the development of an M1, of a mode 1 spoke, as you see in the video on the right. But what we also found out is that this spoke apparently is sonic at the edge. As you can see in the spectrogram on the left, the power peaks are deposited on a straight line, and that line is the ion sound wave velocity computed at the domain edge. We then took the results from these simulations with our scheme and compared it against a finite difference scheme, which has been done extensively in the literature. And what we found out was a good match between the electric potential and the temperature, while the density had some differences. And this is probably due to the different domain geometry in the way that we treat the particles and the noise of the schemes. Now, since we introduced as a new numerical parameter the maximum number of modes included in the model, we wanted to do some convergence analysis, both on the particle weight, and for that we found good convergence. While for the number of modes, we found out that this is deeply tied also with the resolution of the grid. So we still have to go a little bit deeper into this. But all in all, this new scheme seems quite promising, seems quite competitive in the runtime, and it still has to be optimized. So we expect an even more competitive code in the future. But mostly we want to apply it to 3D case, for example, the study of instabilities and transport in magnetic nozzles. And here we're going to see even more advantages, also because we don't have a full 3D grid. And about my scientific contribution, I have 2 peer-reviewed publications that I have described previously in the presentation. I have participated in 3 conferences. 2 of them I participated presentially, and there were 2 instances of the International Electric Propulsion Conference. And in the last one, the Space Propulsion Conference in Bari, instead, my friend Guillermo presented for me. And for dissemination, I participated in 2024 in Semana de la Ciencia and in 2025 in Noche Local de los Investigadores. And that was everything. Thank you for watching.